Hello class, welcome to the STAT 215 Lecture 25 video. In this video, we are going to focus on three tests: the chi-squared goodness of fit test, the chi-squared test of independence, and the chi-squared test of homogeneity. First, we'll begin by looking at the chi-squared goodness of fit test. If we think back to what we've studied the previous week, we learned about hypothesis testing for one population mean mu, the hypothesis test for the difference in two population means mu1 minus mu2, the hypothesis test for the population mean difference mud, the hypothesis test for one population proportion p, and the hypothesis test for difference in two population proportions p1 minus p2. However, hypothesis tests have other applications, such as to determine if a population has some specified theoretical distribution, to determine whether two categorical variables are independent for some population of interest, to determine if populations are homogeneous with respect to a specific category variable, and more. In the chi-squared goodness of fit test, we use this to determine if a population has a specified theoretical distribution. For each possible category of a categorical variable, an assumed probability of occurrence is specified. Our null hypothesis in this test will be the specified distribution is correct. The alternative hypothesis is that the specified distribution is not correct. Let's take a look at an example. Imagine that a gambler wants to test a die to determine whether it is a fair die. The roll of a die has 6 possible outcomes: 1, 2, 3, 4, 5, and 6. And the die is fair if each of these outcomes is equally likely. That is, the probability is 1/6. The gambler rolls the die 60 times and counts the number of times each number comes up. These counts are called the observed frequencies. We can see the outcome of the gambler's rolls in the chart below. In this case, our null hypothesis is going to be that the die is fair. The null hypothesis says that each outcome has a probability of 1/6 of occurring. We let P1 be the probability of rolling a 1, P2 be the probability of rolling a 2, and so on. So then our null hypothesis would state that P1 is equal to P2, which is equal to P3, which is equal to P4, which is equal to P5, which is equal to P6, which is all equal to 1/6. The alternative hypothesis says that the roll of a die does not follow the distribution specified by the null hypothesis, meaning our alternative hypothesis states that not all of the pi are equal to 1/6, where I is equal to 1, 2, 3, 4, 5, and 6. So to test our hypothesis, we need to determine what counts we would expect in each category if the null hypothesis were true. The expected frequencies are the counts that we expect would occur if our null hypothesis was true. If the probabilities specified by the null hypothesis are P1, P2, and so on, and the total number of trials n, then the expected frequencies are E1 equal to n times P1, E2 equal to n times P2, and so on. So essentially, the probability multiplied by the sample size should give us our expected frequency. The table below shows the outcomes of the observed frequencies and the expected frequencies for the 60 tosses of the die. At this moment, I want to pause for a second just to let us recall. So for our expected values, our expected frequencies, if we recall, our EI is going to equal N times PI. Luckily for us, we are assuming all of our PIs are constant at 1/6, and our sample size is 60. This will give us an expected value of 10 for each of our possible roles. That's where the 10 is coming from. We already know where the observed one is coming from. So, if our null hypothesis is true, the observed and expected frequencies should be fairly close together. The larger the differences are between the observed and expected frequencies, the stronger the evidence against our null hypothesis. This leads us to calculating our chi-square test statistic. This measures how large the differences are between the observed and the expected frequencies. We let k be the number of categories, and we let O1 through OK be the observed frequencies, and we let E1 to EK be the expected frequencies. Then the chi-square test statistic is chi-squared equal to the summation of I equals 1 to k of the quantity OI minus EI, quantity squared, all over EI. When our null hypothesis is true, the chi-squared test statistic has an approximate chi-squared distribution with k minus 1 degrees of freedom. Now this is under the assumption that all the expected frequencies are 5 or more, given our sample size. At this moment, let's take a moment to talk about some characteristics of the chi-squared distribution. First, you can notice that the chi-squared distribution is not symmetric. This is an opposite to our normal and t-distributions. Second, the values of the chi-squared statistic are always greater than or equal to 0, meaning you will not have a negative chi-squared statistic. Excuse me. Also, you can use the chi-squared tables from lecture 17 or StatCrunch to find the areas. Now let's talk about the process of performing a goodness of fit test. First, we'll state our hypothesis. Second, we will calculate our test statistic. Then we will find the p-value using the chi-square distribution. Finally, we'll compare our p-value to an alpha, make a statistical decision, and write our conclusion in the context of the problem. So if we move back to sample 1, we've already established our hypothesis. Let's now take a moment to calculate our chi-squared statistic. If we were to plug in each of our observed and our expected values, subtract, square, and then divide by our expected value, and then add up our total, we will get a chi-square statistic of 9.4, for which we will compare to a chi-square distribution with k minus 1. Our number of categories in this case is 6. 6 minus 1 equals 5, which is going to be our degrees of freedom. If we wish to use StatCrunch, we can do this pretty easily by going to Stat, Calculators, chi-squared. We will plug in our correct number of degrees of freedom. Remember, for our p-value, it is as extreme or more extreme, so therefore it will always be greater than for our chi-square test. Then we'll plug in our necessary and calculated test statistic. Hit compute, and we will get our p-value. In this case, our p-value is 0.0941. If we assume our alpha is at 0.05, that means 0.0941 is greater than 0.05. And as we've always done, when p-value is greater than alpha, we do not reject the null hypothesis. And therefore, we can make the conclusion that we do not have sufficient evidence to say that the probabilities of some of the outcomes are not 1/6. That is, we do not have sufficient evidence to say that the die is unfair. However, that does not necessarily mean that the die is fair. It just means we were unable to prove that it wasn't fair. At this time, let's take a look at a second example. Let our null hypothesis be in this case that P1 is equal to 0.5, P2 is equal to 0.3, P3 is equal to 0.15 and P4 is equal to 0.05. In the table below, we can see that we have 4 categories, and then we have our observed and expected values. If we take a sum of all of our observed quantities, we can see that we have a sample size of 200. That is, 106 plus 64 plus 24 plus 6 equals 200. And we can see by having categories 1, 2, 3, and 4, we are obviously going to have 4 categories. Now this leads us to calculate our expected values. Remember, the expected value is the sample size times the probability, or at least our null hypothesis stated probability. This will be n times p1, n times p2, n times p3, and n times p4, which will give us an expected value of 100, 60, 30, and 10. Looking at our observed and expected counts as they are, they don't appear to be too different, but we can't say for sure until we calculate our test statistic. So once again, we know that our null hypothesis is P1 equal to 0.5, P2 equal to 0.3, P3 equal to 0.15, and P4 equal to 0.05. Our alternative hypothesis states that at least one value of Pi differs from what is stated in the null hypothesis. Calculating our test statistic, again, it is observed minus expected squared divided by expected. We get a chi-squared test statistic of 3.427, and we will compare this to a chi-squared distribution with 4 minus 1 or 3 degrees of freedom. If we plug it into StatCrunch, we will get a p-value of 0.3304. Since 0.3304 is clearly greater than our alpha value of 0.05, we will not reject our null hypothesis. This means at the 5% significance level, we do not have sufficient evidence to say at least one PI differs from the value specified in the null hypothesis. Okay, so this brings us to the end of our first objective and on to our second, the chi-squared test of independence. In this test, we consider measuring two categorical variables for a particular population. We want to know, are those variables related to each other, or are they independent? We will follow the same process of hypothesis testing. We will begin by stating our null and alternative hypothesis. For the null hypothesis, our two categorical variables are assumed to be independent in the population. The alternative hypothesis will be that the two categorical variables are not independent in the population, meaning that the two variables are related. Let's begin by taking a look at an example. A study followed a random sample of 8,474 people from 3 locations over about 4 years. All subjects were free of heart disease at the beginning of the study. The subjects took the Spielberger Trait Anger Scale, which measures how prone a person is to sudden anger. The subjects were classified according to whether or not they had coronary heart disease at the end of 4 years. Yes was labeled as 1 and 0 was labeled as 2. And whether they had low anger, which was labeled as 1, moderate anger labeled as 2, or high anger labeled as 3, according to the anger scale. To clarify, this means our null hypothesis was that the anger classification and heart disease status are independent for the population. The alternative hypothesis would be that the anger classification and heart disease status are not independent for the population. In our table, we have our observed frequencies of our anger status and our CHD, or heart disease status. Notice we were also given our marginal frequencies. Okay, so now that we were given our observed frequencies, we can review quickly how to find probabilities of certain events. So for example, the probability that we had a CHD of yes, meaning they had heart disease, we would take the total of the number of patients who had heart disease over the grand total. That would give us a probability of 0.022. Also, if you recall, we can use these tables or frequency tables to tell us about conditional probabilities, such as what is the probability that they have heart disease given that the patient has low anger. So using our low anger total, it would be over the number of patients who are both low anger and have heart disease. So this would be 53 over 3,110. This probability would be 0.017. Next, we were asked to find what is the probability that the patient has heart disease given that they have high anger. In a similar fashion, we will have the frequency of a patient who is both high anger and has heart disease over the frequency of just having heart disease. So 27 over 633. The probability of this event is 0.043. Now, at this point, we can take a look at our test of independence. For this, we need something called the expected count. This is the value we expect in a particular cell if the null hypothesis is true, meaning if the variables are indeed independent of the population. To calculate the expected count, it is the row total multiplied by the column total divided by the grand total. Just to be clear, if I scroll up, 190 and 8,284, these are the row totals. The 3,110, the 4,731, and the 633, these are the column totals. And finally, that 8,474, that's the grand total. We will use these values to calculate our expected counts. For example, the observed count of someone who both has heart disease and low anger is 53. The expected value is going to be 69.7. How was that calculated? Well, it was the row total of 190 multiplied by the column total of 3,110 divided by the grand total of 8,474. This is how we got the 69.7 value. Let's take a look at another example. Our observed count for having heart disease and high anger is 27. The expected count for having heart disease and high anger would be 190 multiplied by 633 divided by 8,474. This would give us an expected count of 14.2. Hopefully at this point you're saying this isn't too bad, it just may take some time. At this point, let's take a look at our expected frequencies table. Let us assume that we've gone through and calculated all the expected counts. We can see this in the table. Now we can check our assumptions. First, we need to have a random sample from the population. And second, all our expected counts need to be greater than or equal to 5. As our lowest expected count is 14.2, I would say we've met all of our assumptions. So we can go ahead and use the chi-square test. At this point, we can calculate our test statistic. Notice our test statistic is calculated the same way as it was in our previous objective. The only true difference besides the way we calculate our expected counts is the degrees of freedom. In this case, our degrees of freedom is the quantity of R minus 1 multiplied by the quantity of C minus 1. R is the number of rows in the table, not including the total column or total row, and C is the number of columns in the table, again, not including our totals. So for this example, we can, because we're fortunate enough, we can either do this by hand or we can use StatCrunch. The thing about using it in StatCrunch, you must be careful and make sure you delete the total rows and columns. StatCrunch will not recognize that those are totals. They will think they're frequencies. So in StatCrunch, you can go to Stat, Tables, Contingency, and select with Summary. From there, you can select under Hypothesis Test, the chi-square test for independence. Also, if you desire, you can select the option of expected count. That will automatically give you the expected counts you could have calculated by hand, but if you're feeling lazy, StatCrunch will do it for you. Then you can click Compute. Once you hit Compute, you will be given your chi-squared value and a p-value, not to mention your degrees of freedom. Of course, as always, in order to make our decisions, we'll compare with our p-value. In this case, our p-value is 0.0003. And since that is our p-value, which is clearly less than our alpha value of 0.05, we can reject the null hypothesis. This will lead us to state the conclusion: at the 5% significance level, we have sufficient evidence to say that anger classification and heart disease status are not independent in the population. That is, anger classification and heart disease status are related. Let's go on and take a look at a fourth example. Are morbidly obese patients at higher risk of dying after a traumatic injury? We will use retrospective medical record review of all patients in a level 1 trauma center over a 1-year period. Our variable for obese will be yes if the patient had a BMI of greater than or equal to 35. No if the patient's BMI was less than 35. The variable for died will be yes if the patient died and no if the patient survived. In this example, our null hypothesis will be the morbid obesity and death from an injury are independent in the population. The alternative hypothesis is that morbid obesity and death from injury are not independent in the population. To begin, let's take a look at our contingency table. Notice we were given both the observed and the expected values. In StatCrunch, if you select to be given the expected counts, they'll be given to you in the parentheses. And in order to check our assumptions, we know that we have a random sample, but we also need to check that all of our expected counts are greater than or equal to 5. In this case, it looks like we check out, barely, since the number of patients who are obese and died was 5.79. So we got lucky. Or maybe not. Now using StatCrunch, we can calculate our chi-squared statistic, which in this case would be 10.492, which would give us a degrees of freedom of 1 and a p-value of 0.0012. At this point, we can now make a decision and state our conclusion. Since our p-value is 0.0012, which is less than alpha, this means we will be able to reject the null hypothesis. This means at the 5% significance level, we have sufficient evidence to say that morbid obesity and death from injury are not independent in the population. Or in other words, they're saying that there is a relationship between morbid obesity and death from injury. I do, however, want to draw your attention to, while we've made a determination of yes, there's a relationship, the chi-square test doesn't tell us the nature of the relationship. So if we take a moment and look at the percentages, it says that 10.7% of morbidly obese people died from their injuries, whereas 4.1% of people who were not morbidly obese died of their injuries. Because of the limitations of the chi-square test, we can't determine directionality, although looking at the percentages, we can have an idea. This brings us to our third test, the chi-square test for homogeneity. For the test of independence, we take a random samples and then the row and column totals for the contingency table are determined by chance. Another application of the same methodology is one in which either the row or column totals are predetermined, meaning we want to compare the distribution of one categorical variable for two or more groups. In this case, the null hypothesis will be that the distribution is the same for all groups, and the alternative hypothesis is the distribution is different for at least one group. Let's begin by taking a look at an example. According to a Johns Hopkins University study published in the American Journal of Public Health, widows live longer than widowers. Consider the following survival rate data collected on 100 widows and 100 widowers following the death of a spouse. In the table, we can see years lived in the categories of less than 5, 5 to 10, and more than 10. And we have our columns for widow and widower. In this case, our null hypothesis will be that the distribution of years lived is the same for widows and widowers. The alternative hypothesis is that the distribution of years lived is different for widows and widowers. So let's examine the test itself. The mechanics of the chi-square test of homogeneity are identical to the chi-square test of independence. We need to make sure all of our expected counts are greater than or equal to 5. We calculate our chi-square test statistic and compare it to a chi-square distribution with the quantity of r minus 1 and quantity multiplied by the quantity c minus 1 degrees of freedom. So if we were to calculate it the same way into StatCrunch, we would get a chi-square value of 5.78. Notice each of our expected counts, as we can see in parentheses, are all greater than or equal to 5. This tells us that our assumptions check out. We have a degrees of freedom of 2. Again, we have our chi-squared value and a p-value of 0.0556. Since our p-value is equal to 0.0556, which is greater than alpha at the 5% significance level, we do not reject the null hypothesis. This means at the 5% significance level, we do not have sufficient evidence to conclude the distribution of years lived is different for widows and widowers. All right, so that brings us to the end of this lecture. Let's just do a quick summary of everything we've learned. We started off by looking at the chi-squared goodness of fit test to determine if a population has some specified theoretical distribution. Then we looked at the chi-squared test of independence, which determines whether two categorical variables are independent for some population of interest. Then we looked at the chi-squared test of homogeneity, which determined if populations are homogeneous with respect to a specific categorical variable. That's it for today. Have a good night.